of data. These are general idea of the statistical method, statistical quantities that are involved in analysis of data, interpretation of data, and the error analysis for this. So in the last two lectures, we discussed about the statistical methods for experimental data analysis. What is data? What are the quantities that are important for a single variable measurement? And if you measure two variables, then how you interpret whether these two variables are correlated or not, how you interpret the data as per this correlation. And then if you have more than two variables, what happens then? And then the next one was a very important thing, which you will know in the next section of the lecture, the distributions, the theoretical distributions that we take help of, theoretical probability distribution that we take help of while interpreting our data. So today we will move on to the next section of the lecture, which is the error analysis. And let's immediately go there. So we get the data. We perform an experiment and we get the data. But before we jump into the interpretation of the data, we have to think of a few things. That is why I start this lecture with, we are so close to the interpretation of the data result of our experiment, yet so far, because we have to think of a few things before we start interpreting our data. And another thing is, we all know about this, but sometimes we mix up these definitions, these words. That's why I call it semantics, which actually deals with different meaning of same words. It's a kind of linguistics. It comes from linguistics. So in this case of analysis of data and interpretation of data, it is very important to know this difference, that is, what is accuracy and what is precision. We often tend to mix these two definitions of the single thing. We sometimes call it is accurate, sometimes call it precision, precise, but what it is. Accuracy is actually the degree of closeness of the measured value and true value. So you measure something, you measure some quantity from your experiment, and you try to see how close this measured value is to the true value. And precision is not actually same as the accuracy. It is the degree of closeness. There is some chat, somebody is saying something, I can't see the chat.
Sir, actually your I think your slides are other slides. It's intro to Beamer and overlaying concepts like that. So
Sorry?
your slides are not not the proper slide, I guess.
What are you seeing?
I can see intro to Beamer.
Oh, sorry.
Yeah.
Sorry. That was probably open somewhere, and I don't know where it is open. I don't know if, okay, let me unshare it. Or how do I unshare presentation? Anyway, so let's come back to this. So accuracy, we are discussing about the difference between accuracy and precision. Accuracy is the degree of closeness to the measured value which you measure, and how close they are to the true value. However, precision is the degree of closeness of the results from repeated measurements of the same quantity. What does it mean? It means that if you measure same quantity many times, then you get different values. But how these different values are distributed in the space, I mean, how close they are with each other. Okay, this is what is precision. So, and then there is another thing which is needed a discussion, that is error or uncertainty. In that definition, if accuracy is the degree of closeness of the measured value and true value, then error, or rather inaccuracy, I will call it, is the degree of deviation of the measured value and true value, right? So how far your measured value is from the true value is the inaccuracy, okay? But uncertainty is the interval around a measured value within which results from repeated measurements fall. So if you measure same quantity many times, then you will see that they are within some interval of the well, I mean, I'll come to in the next slide. You will see what is true value, what is not. But so there is an interval. There is a for example, if you try to visualize that you get 1 point on your white notebook for the corresponding to one measured value, and if you measure the same quantity many times, then this measured value will fall within an interval of the first measurement, okay? Or if you just take 10, 100, 1,000 measurements, all of them falls within some interval. So that interval is the uncertainty. So keep these definitions in mind. Accuracy is the degree of closeness of the measured value and true value. So error or inaccuracy is the degree of deviation, how far apart is your measured value from the true value. Whereas precision is the degree of closeness of the results from repeated measurements of the same quantity, and uncertainty is the interval around the measured value within which results from repeated measurements fall. So you immediately can relate precision and uncertainty. So if uncertainty or the interval is very small, then you can call it a precise measurement. The uncertainty or the interval, if it is very large, then you can say that your measurement is not precise. Am I clear about these 4 terms? Because this is very important to start your discussion of error or of any data that you interpret. Am I clear? Please. I don't hear anything. Am I still audible?
Yes, sir. It is clear.
Okay. Okay. So this is how you can you can represent it in a graphical way, that in the x-axis you have your measured value, in the y-axis you have the probability density. That means you by now you know from the previous 2 lectures that what is the probability density. So how many times your measured value falls, that is practically the probability density, and your reference value here is actually the true value I'm talking about, and the mean of this. So this, for example, when you talk about the measured value, so they follow some kind of distribution. Which kind of distribution it is and why it is so, we will come in this lecture later. But the mean value or the most probable value, so to say, the most probable measured value is denoted by this vertical line, and the distance of this vertical line to the reference or true value is the accuracy from this definition. This is the degree of closeness of the measured value and true value, and it is the same as the inaccuracy. So if this distance is quite large, then it is inaccurate measurement. However, the precision is quantified by the spread of this distribution, So if this is wide, the spread is wide, then it is imprecise measurement, and if the spread is narrow of this distribution, then it is precise. You can represent it in another way, that is this. So you see there are 4 pictures. So this is the picture of, so you can imagine that the bullseye, you must have seen at your own eyes, or picture of this in when you see these Olympic events or the games events, archery, either archery or shooting. Then there is a bullseye. So this is the center of the bullseye, and every archer or shooter aims his or her arrow or the rifle or pistol to shoot at this bullseye. So it's called bullseye. I don't know, for whatever convention. He tries to shoot here. Okay. Now, in reality, it does not happen always. So sometimes, so this there can be 4 situations like this. Okay. In one situation, in from one archer's arrow, a bow, or the shoot or the rifle or pistol, the bullets or the arrows are falling here. So this is low accuracy. So it is farther, much farther from the actual target. The bull said that somebody, sorry, somebody is talking, asking something. No. Okay. So in this case, the arrows or the bullets are distributed over here. So all of them are very far away from the actual bullseye, and all of each of them are farther, I mean, far away from each of them. So so one is very far from the other. Okay. You actually cannot group them together. Okay. The second picture is these arrows from a different archer, or from maybe from a different from the same archer in a different round. So there are rounds: first round, second round, third round. In this case, his arrow or the bullet are centered around the bullseye. Okay. So you can say that this archer or shooter has aimed very accurately. They have landed up very accurately, but precision is not much, because you can see that these black dots are there's a clear distance between each pair of black dots. Okay. The third case is this guy, or in this event the same guy is very precise, but unfortunately his target where it has landed up, the point is far away from the actual target. So it is very precise, but very bad, very inaccurate or low accuracy, so to say. And the fourth case is the winner, is the gold medalist. So he or she shoots all his arrows or bullets right at the bullseye. So it is very high accuracy and very high precision. So our aim as an experimentalist is to win the gold. So we will always aim to make such a measurement. However, let us see how we fare, how we get it. And finally, whatever you do, so this is live, you see, not even the gold winner always hits right at the bullseye. So whatever precision you aim to, finally in an experiment, like in the event of an archery or shooting, you don't really end up right at the center. So there is a spread. However high precision the data is, there is a spread. So that spread you have to quantify and quote with your final result. Otherwise, your result is incomplete. So unless you tell that you have measured some quantity with some interval where all your measured points have fallen, it is incomplete and it is unbelievable. Nobody will believe an experimental result which does not have an uncertainty assigned to it. So I call it uncertainty. Why I call it uncertainty, you will see. My question is then we are making a mistake? So I said I wanted to measure something, and then I say that I don't measure it right, the exact value always. So are we making a mistake? But then my question would be, do we actually know the true value? We are doing an experiment. If we know the true value, then we would not perform the experiment otherwise, right? You are measuring something, you are doing an experiment to know the value. You do not know the true value. You can argue, sir, some calculation has given this, so I'm measuring that. In that case, you know the true value, but finally you are measuring from it you are measuring it from your experiment, and it may so happen that the calculation was wrong. That was not the actual true value. Then if you believe, if you trust, if you believe in a blind way that that is the true value which has been given by the theory, then once again there is no point in doing the experiment. Then it's done. So you don't do the experiment. So you, when you do an experiment, you have a base value in mind, but you believe in what you get in your measurement. So we actually do not know the true value. True value will emerge from our experiment, your experiment. Well, then we should not talk about the error, right? If you go back to the last transparency, we defined error as the distance from the true value, between the true value and the measured value. So if we do not know the true value, then we do not know the error by definition, right? We should not talk about an error, right? Well, we are often sloppy. You see, the title of my lecture is error analysis. We all call it error analysis. Even the books, the literature, the lecture notes, the papers, they all talk about error analysis. So this is, I would say, this is a sort of sloppiness. We actually should not talk about error. Then, so let's get it straight. Uncertainty is not an error. It is not a mistake. It is not a blunder. You have not done anything wrong by making a measurement, by getting a value which is away from your last measurement. It's not a blunder. It is caused from it is not caused from incorrect handle of equipment. So if you get an uncertainty that is not really, your supervisor cannot tell you that, okay, you do not know how to handle the equipment, that is why you got it. Nobody can tell this, because rather it is a practical way to quantify the result of an experiment. As I said, you have seen it, that a shooter's arrows, bullets or arrows do not reach the bullseye always. So that's what is life, and this is actually true for an experimental endeavor, true that it is not incorrect. And so this is the quantity we are interested in. We are actually not interested in an error. We are interested in uncertainty, and that is the quantity that we should relate to our experimental finding. Okay. So from now onwards, I will talk about uncertainty, not error, because this is not a mistake. Okay. So uncertainty, what is uncertainty? Uncertainty is a measurement. In a measurement, usually creeps in through two different ways. And why uncertainty actually happens, actually occurs. I expected that my experimental result will be the exact true value. Why does it happen actually? Due to some instrumental calibration. As I keep it in mind, it is not wrong. It is a wrong calibration or use of different instruments to measure the same quantity. If you measure a quantity with an equipment which is calibrated wrongly, it is not a wrong instrument, it is calibrated wrongly. That is why you get an uncertainty. Or use different instruments to measure the same quantity. If you measure the same quantity with two different instruments will give you similar, very close, but not exactly the same result. And that results in your uncertainty in the measurement. So for example, a metal ruler for measuring a length on different days. You measure a length with a metal ruler in a day of December in Geneva and use the same metal ruler in the summer days in Rajasthan, Jaipur. What will happen? The ruler, the length of the ruler will not be same at 20 degree or 18 degree in Geneva and 45 degree in Jaipur, right? So in that case, the gradation, the graduation on the scale or the calibration will be different. So you'll get a different result. Okay. And then more close to your experiment, if you use different tracking algorithms to detect particle tracks, you'll get an uncertainty. If one algorithm will give you some tracking, some tracks particles as tracked, I mean some signals as tracked, the another one may not give it or give a different number. So if you have 100 tracks, one type of algorithm will give you 95, another type of algorithm may give you 97. Okay, but then you can imagine that if you just shift like the temperature, it is shifted in one way only, from winter to summer, so the length has increased. So if you measure a length 100 times in Geneva, and if you measure the same length 100 times in Jaipur, then all 100 measurements will be shifted in one way, right? Okay, so similarly, if you use a different tracking algorithm for 100 tracks in one event, one gives you 95, another gives, if you once again employ the same two different tracking algorithm for another 100 tracks for another event, it will give you similar number. So it is systematically shifted in one direction. Your result, your final result is systematically shifted in one direction. And this is what is called instrumental or systematic uncertainty. You can have systematic uncertainty due to many things based on what I said. Instrumental wrong, I mean different instrumental calibration or different instrument to, so the second one is the different instrument to measure the same quantity. Different tracking algorithm is different instrument to us. However, there is another type of uncertainty due to the randomness in either the process resulting the quantity that is measured or in the process of measurement itself. It is the randomness in the process or process resulting the quantity that is measuring, that we are measuring. Whatever we are measuring, if it is produced randomly, then your measurement will be random, right? We will have different results. So you are actually not measuring exactly same thing every time. So that gives you some uncertainty. Or the process of measurement itself involves some randomness. Okay, for example, the same ruler is used by different people. That means the way one person is looking at the scale at the graduation is slightly different from the other person. Somebody may have a parallax. Okay, but now if you employ 100 people to measure the same length with the same ruler, some will measure it little higher, some will measure it little. So for example, I said that you measure 100 times a length in Geneva. If this 100 times is not with same experimenter, is with 100 other different people, then some of them will measure it little higher, some of them will measure it little lower. Okay, that is what is the randomness. So like counting the decays from a radioactive source. So you know that a radioactive source producing the decay itself is random. It's not exactly the same every time. So then that gives you that kind of thing, or any other source that gives rise to change in result in random way. That's what I explained in the last sentence, that if you employ 100 people to measure the same length with the same ruler, you are not changing the calibration. You are sitting at the same temperature, same day. In 10 minutes, 100 people measure the same length. Even then, there is a randomness in the result, and these will gives rise to statistical uncertainty. This is what is called statistical uncertainty. And there is a difference between these two. The first one can only be estimated. Unfortunately, it is not very simple to estimate unless you know the proper calibration or the temperature or etc. The situations. It is very difficult to estimate. However, it cannot be avoided, because if you do this, if you measure, if you use the same ruler in one place where the temperature is 15 degrees and one place where the temperature is 45 degrees, you cannot avoid the change in length of the ruler. You cannot do this. So you cannot do anything. You just have to know this and quote this number, you quantify it, and that's it. However, the statistical uncertainty, the other type of uncertainty, can not only be determined using the distributions, these are the distributions which we discussed earlier, and can also be minimized by taking large number of measurements. If you take large number of measurements, so for this calibration thing, if you whatever large number of measurements you do, you will not be able to avoid this. But for statistical uncertainty, if you take large number of measurements, you can actually minimize them, minimize this uncertainty. That is the essence of it. Okay, how this statement is true, that if you take large number of measurements, it is minimized, will come in the course of discussion. First, let us discuss about the systematic uncertainty. And you see, there is not much to discuss because this is very straightforward. You cannot do much of it. So you just identify all possible sources of uncertainties. For example, one source, as I said, is the calibration. Estimate the uncertainty for each of the sources, and then if the sources are independent, fortunately in most cases they are independent. They don't, for the sources of systematic uncertainty do not depend on each other. Add the contribution in quadrature to obtain the total uncertainty. This why it should be added in quadrature also will come in the in due course in the discussion. One example of this is, for example, you are measuring a charge jet, properties of charge jets in PP collision, for example. Then you may have sources of systematic uncertainty such as the tracking efficiency. If you change tracking efficiency, if you use different tracking efficiencies, you get a uncertainty related to this, because different algorithm gives you different efficiency. Momentum resolution. If your momentum resolution of one tracking algorithm is different from the other, that gives rise to one kind of systematic uncertainty. The reconstruction, jet reconstruction algorithm itself, if you use different type of jet reconstruction algorithm, they give you different results, but all of them are systematic. So if you use one type of jet reconstruction algorithm to reconstruct jets for 100 events, they will give you similar. Okay, but if you use another type, they will give you similar, but which is little bit different from the other one. This is what is called systematic uncertainty, and you just do this, estimate what is this difference of different results, and that is your systematic uncertainty. You get them, you add them in quadrature, you get the total systematic uncertainty. You cannot minimize it, you just have to determine it and quote it with your result. And this is enough to discuss about systematic uncertainty. You can discuss what is the source, where from it comes, but everything depends, everything lies in this identifying all possible sources of uncertainties. And here you actually have a kind of knowledge of what are the sources. You have to think of what can be the sources, which source you are leaving, which source you are not including. This is the most important thing. Rest is simple. Okay. Next is, what is the limiting distribution? So this is we are entering into the realm of statistical uncertainty, and what is the limiting distribution? That is the question. What is this? This is, for example, somebody is measuring the number of counts from radioactive decay, and he or she counts for each 2 seconds interval. Okay, and he or she takes hundred of these measurements. So 2 seconds interval, 100 times it takes, and then gets a distribution like this. Because you see, you keep in mind that it cannot be 0 or less than 0. There will be within 2 seconds, even if it is 0 all the time, then you do not take this interval, right? If you don't get any signal on your GM counter, you do not take this interval. So you take interval, such a small interval where you get some counts, but it cannot be 0. So it will be somewhere close to 0. In 2 seconds you get something, and then for 100 of these 2 seconds interval you measure, it follows this distribution. Okay, you see, this is actually a Poissonian distribution. We discussed in the last class that this type of thing are Poissonian in nature, and this is a Poissonian distribution. If you think this distribution, this follows the Poissonian distribution. However, now let us discuss consider a second case where the same experimenter, same equipment, same thing, just increases the interval to 10 seconds. Instead of 2 seconds, the time interval is changed to 10 seconds. Let's see what happens, or 15 seconds here. So here you see, as soon as you increase the interval to 15 seconds, you get large number of counts. And as you get large number of counts, because in 2 seconds you get 2, 4, 3 counts, and here you get something like 10 counts on an average. You see, you already see the change in the distribution. Okay. Why this has happened? This has happened because here your n within an interval was very small. As you increase the n, you remember, for an increased n, your Poissonian boils down to Gaussian. So this is still a Poissonian, but it is going towards Gaussian, right? Okay, same thing, but here what we discussed is that the process of radioactive decay itself is random. You do not know the probability when it will decay, when not. But if you take enough amount of measurements, so this you have increased your interval to 15 seconds, and you have taken enough amount of n in the event inside, so it becomes Gaussian. Similarly, in a similar way, a measurement which does not follow any a priori distribution, so to say, you just measure, as I said, that you measure the length of a line with a ruler, but 100 people. What happens if you have 100? If you measure 100 times, then your distribution looks like this. So maybe the length is 25.5 or so, but then you have a distribution which is like this. You see, this is far from a regular shape of the distribution. You just employ 10 times 100 people. So you make your n 1000, you see already it takes a kind of smoothened distribution. The mean has shifted not much. It is 20, it is here the most probable value may be 24.8, here it may be 25. The mean has not shifted, but the distribution has now become much smoother. You see, the importance is not only the mean, the importance is the spread. So here calculation of the spread will not be easy, but if you take this the right hand side graph, your calculation of the spread, so your mean measurement is still 25. It was 24.8, it has now become 25. It's not much different, but if you try to calculate the spread here, it will be much more difficult than here, because you already know that this is Gaussian and you can calculate the spread of a Gaussian, the sigma of a graph. So this is why I said that if you make more number of measurements, it is easier to find the spread. And later on we will discuss that if you make even more number of measurements, your spread becomes smaller. So what does the mean lie? Where actually, so I said the mean moves from 24.8 to 25. So where actually does the mean lie? The probability that any one measurement in X yields a value in the range X is in between a, b, is integral a to b fx dx. This we calculated in the last class, where fx is the limiting distribution, whatever the distribution is. Okay. When the limiting distribution is a Gaussian distribution, as I said, if you take enough number of measurements, Poissonian distribution, or rather any distribution, they tend to go towards Gaussian distribution. So if we take that the limiting distribution is a Gaussian distribution, one can actually calculate the probability of the result. There is a spelling mistake. Of the result will be in the range x minus sigma to x plus sigma, this can be calculated from this, because this is your Gaussian probability distribution. Okay. With the standard Gaussian distribution, this is also so this is x minus mu over sigma is replaced with z, and if you replace this, then with standard Gaussian distribution, the same quantity, this becomes this. Okay. What is the usefulness of this? We'll see. For any interval, so for example, we said that x minus sigma to x plus sigma. What happens if it is x minus 2 sigma to x plus 2 sigma? What happens if it is x plus 3 sigma minus 3 sigma to 3 sigma? Then let us take that in general, if it lies between x minus t sigma to x plus t sigma, the integral takes the form this. Now I have a question to you and you have to answer. Do you know this? Have you seen this? This has a name? Do you know the name? Anybody? This is a standard integral. You see, when you did integral, when you learned integral calculus, there were some standard integrations, standard integrals, and this is one of them. And this has a specific name. When I'll say, then, or if you know the name, tell me. If nobody knows, then say no, we do not know. We have not heard this.
Gaussian integral.
No, this is not Gaussian. Gaussian is the earlier one. This particular thing has a name.
So error integral.
Who is this?
Protyaya, sir.
Protyaya. Fantastic. This is what is called error integral. And you now will slowly, you have already guessed why it is called error integral. When you knew the name, did you know this? I guess you did not. But now you know why it is called error integral. Because if you see, there are two. See, if you just plot, yeah, okay. So first thing is, this cannot be solved analytically. This has to be done numerically. Numerically, it is possible. In a computer program, you can calculate this, the value of it. And if you do that, and if you try to plot this, that this is the probability in the y-axis is the probability within within 1 sigma, and this is your sigma. So if you plot this, the curve looks like this. So what it means is, in 1 sigma, this is the second dotted line, it is called 1, the probability falls from 100% to 68%. If you go to 2 sigma, it falls from 100% to 95.4%. And if you go such so and so, with 3 sigma it is 99.7%, something with 4 sigma it is 99.99%. And same thing is represented here in the right hand side picture. If it is a Gaussian, then this is the mu, and the value lies 68% of the time within mu minus 1 sigma to mu plus 1 sigma. Right? My question was, where does the mean lie? So 68%, if you tell your sigma, and if you say that this is minus 1 sigma to plus 1 sigma, 68% times the mean will lie within this. Okay, the value will lie within the mean, from the mean and plus minus 1 sigma. Whereas 95.4 times it will lie within 2 sigma, and 99.7% or so it will lie within 3 sigma. Few years back, there was a furor, I mean, I would say, in the community, that a boson which has a mass of something like Higgs boson has been seen by CMS. And I also have come to this, that they are quoting the value with 6 sigma. What does it mean? It means that the value lies at a point which is away by 6 sigma from mu. That means no future measurement or no statistical analysis can predict this value. So this is something very new, right? If you do not say this sigma, your mean and the sigma, then you cannot quantify how significant it is. This is your confidence level. This is your confidence level. See, if you increase your sigma, your confidence level is more. As simple as that. Because if you confine yourself to be within 1 sigma, it is only 68% times that it will fall inside. The value will fall inside. If we include 2 sigma, it is 95% that it will, I mean 95.4%. And for 99.7%, it goes to 3 sigma, something like this. So somebody is quoting a result by 6 sigma. That means that no statistical analysis gives a value like this. So this is much further away from all other random error considered to be within this measurement. So that is where the sigma or 1 sigma, 2 sigma, 3 sigma, this kind of nomenclature, this kind of language comes into play. Okay. So this was for one variable. If you measure one variable, then what happens? Suppose you measure more than one variable. Okay. So x is a function of at least 2 measured variables. I mean, life is not always that simple. I mean, no, almost never that simple that you just measure the line of the length of a line and your experiment is done. Those days you have left in your school. Okay. So now you have to measure something. You have to measure 2, 3, 4 quantities, and then finally you have to give your final result, because the final thing is a function of many other things. So let us discuss what happens if there are at least 2 variables and your final result is a function of these 2. We may assume that the most probable value of x, which is the x bar, can be given by function of u bar, v bar, which are the independent variables. The uncertainty in the value of x could be determined from the spread in the individual measurements of u and v. Like the mean was determined from mean of u and v, then the spread can also be measured from the individual measurement, because for spread you need the mean value and the individual measurement, right? So mean can be given by this, and spread can be given from individual measurements of u and v. And how it is? If the number of measurements tend to infinitely large, then we obtain the variance sigma square x is like this. This you have learned in the last class. What is the variance? Okay. So the variance is given by it is given by the sigma square, which is the squared of deviation from the mean, sum of the squared of the deviation from the mean, that we have discussed earlier. Then the deviation in x can be extracted from variations in u and v if you expand them by Taylor's expansion, like this. Okay. So xi minus x bar, that is the deviation of xi from x mean, can be given by this. This is a simple Taylor series expansion of u and v. And then what happens is, from these 2 equations, sigma square x, you know, and here you put the values of xi minus x bar here. What happens is, this is just this. So you still have 1 minus n, then this is your xi, this is like this. Okay. And then just square them. You have a plus b whole square. This is a square plus b square plus 2 into a into b, and then if you have more terms, you will have more terms like this. Just we are considering 2 terms here. Okay. But then you can still write, in case of sigma x square, it was x, so you just replace u and v there, and then you get these 2, sigma square u and sigma square v. Once you get them, you just replace these things. So here you see, this is sigma square u, this is sigma square v. Okay. Replace them and rewrite the equation 40 like this. So you have sigma square over here, dx over du. So this does not have any turning index, so it comes outside the summation, and you get this. Okay, here you see this is your variance. This is v. This is sigma v square. Not this is sigma u square. This is sigma v square. Del x del v, and this term is the covariance. If the measurement, if the fluctuation, if the spread in u and v are correlated, keep in mind I am saying that the deviation, the variance of u and v are correlated. I am not saying u and v are correlated. I am saying deviation in u and v are correlated. Then if they are uncorrelated, then this term vanishes. If they are correlated, only then this term dominates. Okay, right? And this formula is called a general formula for propagation of error. Now, if you know u and v, and if you know the relation among u and v, how they are related in your actual x, what function of u and v is there in your actual x, then you can propagate the error. This is the sigma square u is the error in u, sigma square v is the error, or sigma u or sigma v is the error in v. Then you can propagate this and finally get, your aim is to get sigma x. This is how you can do this. Let us take specific cases, something like this. Let us assume that x depends on a measured quantity u. There is nothing, there is a constant and u. So what will happen? It will happen that then the del x u is del u plus del a del u. But then del a del u, a is a constant, is 0. So del x del u becomes del u, which is 1, and we obtain sigma x, sigma mu. Sigma u is the sigma x. That is implicit, right? Because you have only one variable. This is practically the one variable. And you have the, if you know the error in this one variable, you know that is the error in your actual measured variable. If there is a constant, we don't care. As simple as that. What happens if there is weighted sum? So x is weighted sum of u and v. X equal to a into u plus b into v, where a and b are constants. I think this is very simple. You can do it yourself. Then del x del u is a, and del x del v, once again this is my mistake, I'll change it in the final lecture. Note that this is v, and by substituting these values in equation 41, which is the general error propagation equation, equation 41 you have to keep in mind always by heart. That is the equation for general equation for error propagation, which gives you sigma x square equal to a square sigma u square plus b square sigma v square plus 2ab sigma square uv. Once again, this dominates when, only when the measurements in u and v are, the variance in u and v are correlated. Okay, there are 2 points to note here. The first point is the variance of x, which is sigma square x. You can if you closely see this equation, you will realize that it may vanish if this correlation term has proper magnitude and sign. That means by means of this is a quantity and this is another quantity. Okay, so if this becomes negative and has the same magnitude, similar, I mean whatever magnitude, to match the magnitude of this and this, your sigma square x may vanish. It's very interesting. So if you are measuring u and v and you are trying to get sigma x, sigma of x, you are measuring u with sigma u, v with sigma v, and you are trying to measure sigma x. But then if there is a correlation term which has, I mean, by whatever I don't know, coincidence, has a proper magnitude and sign, then this may vanish. So you don't get any variance in x. It may so happen. And the second point is very important. We all always say that errors are added in quadrature. Why? This is exactly because of this. You see, you are adding the errors in quadrature. I said in the slide where I showed the systematic uncertainty that you add in quadrature. This is exactly because of this. All errors always, almost most of the cases. So if you have this, you have to add them in quadrature. So this is the famous, I would say, addition in quadrature rule. And if you add in quadrature, there is an advantage. You see, the advantage is this actually minimizes the spread. If you just think of, if you calculate, if you take a numerical example, you will see that if you square them, that the variance actually reduces. Okay. Am I audible? I don't see any, I don't hear anything from the other side, so I don't know whether what I'm
Yes,
saying is completely
you are
going out
audible,
of
sir.
the head, or you are really enjoying it. I don't know. Okay, so please sometimes say something so that I know that you are awake. Okay. Okay, so then I'll give you a long list. So you know the equation 41, that is a general rule for error propagation, and you can now work out at home and yourself that your x can have relations between u and v many ways. Like this is a multiplication, this is a division, this is a power law, this is once again another power law, and exponential, this is another power law, this is logarithm, this is trigonometry. So these are sort of some general relations where your two quantities u and v, or a single quantity or whatever, may be related, and then the final thing is your what you are trying to measure, and then you get the sigma on x in such a way. So you just I will not go for each of them. I'll just say that this is you can do it at home, and I'm sure that you can do this. I'll be happy if you do that and send it to me. Okay, that will be up to you. I mean, this is not a school that school. I mean, it's called a school, but it's a school for PhD students. So I don't expect that I have to tell that unless you do this, you'll be fired. Okay, so it's up to you. But this will be a good exercise to do it at least once by hand, so that you just keep it in mind every time you do this analysis, this sort of things. Okay, now we are okay. So this is another problem which I will again not discuss here, but you can do this problem based on your this error propagation formula. If the radius is determined to be r equal to 10 plus minus 3.3 centimeter, what will be the relative uncertainty in the measure of the area? Okay, of a sorry, this is a circle, area of a circle. Okay, so if you measure the radius and you measure it with this uncertainty like plus minus 0.3 centimeter, so what will be the relative uncertainty of in the measurement of the area of the circle? Okay, I am not going to derive this, it is for you, you solve it. Okay, now for example, what is the standard? So we have discussed about the mean, where should the mean lie within 1 sigma, 2 sigma, etc. But what is the sigma? How do we measure the sigma? So measurements of x, we always take that the measurement of x follows a Gaussian distribution with a mean x bar and spread sigma. The spread of x bar, that's what we are interested in, where x bar is this, right? You measure x n times, x a quantity n times, and every time you get a different result, right? So you, for example, you measure once again the length of a line. Every time you get a new result, and then you measure n times, you get average like this. Okay, then what will be the sigma of x bar? That is where we are interested, standard deviation of the mean. Let us go back to the I think this is wrong, not whatever. This is the general error propagation formula. I have to check whether this equation number is right or wrong. But this is from the general error propagation formula, that this is sigma of x bar. So sigma of x, so this is addition, right? So sigma of x bar would be sigma square of x1 plus del of x bar over x1 whole square, plus this is 2, sorry, this is once again, this is 2 sigma x2 square and del x bar x2 whole square, plus there will be many terms like this up to n, right? This will be, there will be many terms like this up to n. But then x1, x2, x3 are all measurements of the same quantity x. Okay, and we said that the x follows a Gaussian distribution. So the widths of this distribution will also be the same. They are Gaussian. So if if you follow the same, if you make the same measurement, your sigma is also the same. So sigma x1 equal to is equal to sigma x2, and for all these n terms, it will be same as the sigma x. Okay, that's the spread of x. Then the partial derivatives are also the same as this equal to this. See, if you do a partial derivative delta x of x1, what will be? The rest are all other terms, right? So independent of x1. So each measurement is independent. Each time, for example, 100 people are measuring with the same ruler. Each people's measurement, each person's measurement is independent. So rest are all 0. So you get only 1 over n, right? So for all terms x1, x2, the delta x or delta x bar of x1, delta x bar of x2 is equal to 1 by n. Then if you put these values here, what you get is this. So sigma x bar, that is the spread in the mean, is the spread you measure for one measurement divided by square root of n. And this is very, very important in the analysis of statistical uncertainty. I mean, if you ask your supervisor or your senior, I have measured it so many times, what is the statistical uncertainty? You'll say, okay, it is 1 by square root of n. And this is why it is 1 by square root of n. You must have heard it, but I don't know whether you have derived it this way or you know why it is this way. This is because of this. So this is another famous rule of 1 over square root of n. So the uncertainty goes as 1 by square root of n. Okay, there will be another question. I think somebody asked me in the first class that what happens to the covariance of only 2 points? There is no covariance, there is no correlation. If you just get 2 data points, how do you measure the correlation of these two? You have to measure n number of points, only then some of them will be, I mean, only then you can measure the correlation. I come back to the same question here. Somebody asked that I make a single measurement, I just make one measurement of the length. What happens to that? What is the uncertainty in a single measurement? Can I quote an uncertainty? Because every time till now I am discussing, I am saying that you have to make n number of measurement, and as n goes, you make your uncertainty becomes. And you see, if n goes high, what will happen to this? This will go low, and that is why I told you that if you make large number of measurements, your uncertainty becomes lower and lower. So that is why we always tell that, okay, you make as many measurements as you can, only then you can minimize your statistical uncertainty. And you must have seen, I mean, I don't know, some of you must have seen that if you plot a spectrum towards the higher tail, you get your statistical uncertainty is large. Why? Because towards the higher tail, you get lower number of measurements, lower number of measure points. That is why your error bars, the vertical lines are longer, larger there. So this is why it is like that. Okay, Raghu is waiting, right? Yes. Oh, okay. Just one transparency, one slide. So what is this? What is the uncertainty on a single measurement? So we do not have a distribution, right? It is a single measurement. So we need to use the analogy, why we do this, how we do this. Experimental data correspond to either Poisson or Gaussian distribution. But if you here, as I said, that for large number of measurements, it is a Gaussian. So even for that, for Poisson, you have sigma square is equal to mean, right? For Poissonian, it is sigma square equal to mean. So that is sigma square x is equal to x bar. For a single measurement, what is the x bar? What is x bar? So you have only one measurement, right? So your n is 1. So sigma x bar is equal to x, right? X bar is x1 plus x2 plus x3 divided by n. Divided by 3, and if you go to n, it is n. In this case, n is equal to 1. So x bar is equal to actually x. So for single measurement, the uncertainty in sigma x is square root of x, right? Sigma x square is equal to x bar. So sigma x is square root of x bar is equal to x. So for a single measurement, the uncertainty is square root of x. So you actually can quote an uncertainty even for a single measurement from an analogy, of course. So you can claim that I have measured it very nicely, so there is no uncertainty, but that is not true, because you yourself, if you measure another time, you may not get the same answer. So that is why you are it is better, it is always prescribed to quote an uncertainty even for a single measurement, and you can do this. So the relative uncertainty for this case would be like this, 1 over square root of x. So if you make a large, if your measured quantity is very large, then the relative uncertainty is low. Only that. So you can say that. Okay, so I am left with 2 other subtopics here. So I have discussed today the what is the definitions of error, accuracy, and precision. How we can measure the error in uncertainty in single variable. How you propagate this for more than one variable, right? And then in the next class, I'll try to discuss about the fitting and how you test whether your fitting is good or bad. That's it. And I have given you some homework, and I don't know whether you are still awake or not, because I don't see, I don't hear anything. I hope you will have fun in working out those examples. Thank you.
Thank you, Supriya. So today actually Professor Raghunath Sahu have another meeting. So at this moment we will not be able to take questions, but you can write to Professor Das if you have